Hey, how are you? This is Luke from Cocos. In the last video, we introduced you to shaders and the foundation and concept of webgl. To summarize, webgl works with the GPU in two ways. The first is to convert vertices into crop space coordinates. The second is to draw a pixel point based on the results of the first part. This chapter focuses on the role of vertex shaders and fragment shader in the rendering pipeline flow, and I will render a triangle as an example, so everyone can gain some knowledge on rendering. So let's first build a new project. Next, we need to create a folder called shader. Of course, you can also create this folder in any way you want. This folder is to include two files, an HTML file and a JavaScript file. I named them as shader. After pairing these two documents, we can start to write our code. Before we start writing graphic drawings, you must enter some vertex data for webgl. If you want to render a flat triangle, just specify 3 vertices. Because it is a flat triangle, there is no depth in Z, so use the two-dimensional position definitions. Eventually, they are stored as an array. The figure shows the coordinates of these 3 vertices I defined for the triangles. There is also a reason why such a value is used here. As mentioned in the last video, the main function of the vertex shader is coordinate conversions. Conversion of the vertex coordinates to crop coordinates. We can control this step. This GPU is processed by cropping the perspective culling to obtain the normalized device coordinates NDC. The perspective culling method divides all 3 components of the vertex in the culling space by the W component. The implement crop coordinates to NDC. Every component of the NDC is between -1 and 1. The excesses will not be rendered. So in the game engine, regardless of the use of local coordinates or world coordinates, you need to convert coordinates. The GPU will eventually convert the NDC to screen coordinates and pass them to the raster. Because this chapter focuses on the rendering process, don't use local coordinates or world coordinates in the game, but use crop coordinates directly. Next, let's look at this picture. This figure is a triangle drawn with NDC, with a set of vertex data. You can see it sends an input to the first stage of the graphical rendering pipeline, the vertex shader. It creates memory on the GPU to store vertex data, then combined with the vertex combination to resolve the memory. WebGL manages this memory through the vertex buffer object VBO, and it will store a lot of vertices in GPU memory for vertex shaders to use. So let's start writing code. First, let's submit vertex data to the GPU. Let's also enable scripts in HTML. First, create an executable function, main. I will write all the drawing instructions in the main function. The next step will be drawn by the GL. In the last chapter, we said that the most elements of the WebGL can be described by status. The state is called by GL to switch. The GL points to the drawing context. The drawing context is obtained through the carrier of canvas. So we must first create canvas, then get the drawing context. Then get a body element. Add the newly created canvas as a child element of the body. Then define the size of the canvas. Here I want to use a canvas size of 400 by 300. Then get the drawing context GL. Get the drawing context through canvas. Context types are divided into 4 types. 2D rendering, bitmap renderer. This is a function that converts canvas context to specify image bitmap, and we'll ignore that for now. Then WebGL1 and WebGL2. Cocos Creator is 3D rendering, so we can choose either WebGL1 or WebGL2. Then determine whether the current browser supports WebGL. If WebGL is not supported, the execution of the current function returns. Some developers may have questions here. Why do I need to manually create canvas instead of directing canvas directly in the HTML file? This is because manually created canvas can let the current script know its type. Custom canvas elements here through HTML. And then when I get it here, I prompt that it's of type any. I can't get any code hints from anything. So even if I created this GL context, I also can't get its API more easily by the way of GL point, and must be used by a pure manual input. Then we start editing the Vertex shader. First, define the shader text. Because it's not possible to use the coloring language in GS scripts, but GL supports the transition of text into shader. So here is a coloring text. You receive a vertex position input, then pass it to the GL built-in variable GL_position. Because GL_position is a vec4, and the vertex position of our entered A position is a vec2. Therefore, it is necessary to convert the vec2 into a vec4. So the x, y, and vec4 comes from A position. Due to having no depth, z is 0. Then the W component is set to 1. Then start creating the vertex shader. Here it receives a type because we are using vertex shader. So use vertex_shader. Then put the vertex colored text to the vertex shader. Then compile shader. Then determine its compilation status. Judging the success of the compilation can be used. If the compilation failed, it informs us that the cause of the error is, and immediately modify it. No fault tolerance can be made here because coloring programs need to be provided in pairs. If a shader has a problem, then the program will not be executed. It must be modified until it's correct. So in this judgment, if it fails, we print the failed log information. Then remove the wrong shader. Since the fragment shader also needs to perform the same method, I extract this part of the content. The create shader method also takes several parameters. The first is the GL parameter. The second is its type. The vertex shader is also a fragment shader. Let me fix some code. Then we judge as long as it succeeded. We then return the current shader. Otherwise, print an error message. Next, define vertex data. This was mentioned earlier. Next, create a vertex buffer object. In the previous content, create a memory store in the GPU in the vertex shader phase. The vertex buffer object is used to manage this memory. It stores a lot of vertices in the GPU memory. The advantage of using this cache object is that we can send a large amount of data to the graphics card at once. So instead of sending once every vertex, sending data from the CPU to the GPU is slow. So whenever possible, we try to send as much data as possible at once. Of course, this data is sent to the GPU memory. The vertex shader can visit these vertices almost immediately, so the speed is very fast. The buffer type of the vertex buffer object is GL array buffer. WebGL allows you to bind multiple buffers simultaneously, as long as they are different buffer types. That is to say, the same type is bound to be bound before replacing. Then we transfer vertex data to array buffer. Data will store the binding vertex buffer. Buffer data is mainly to initialize data storage for buffer objects, because this is the time to pass data to the vertex buffer. So array buffer is selected. The second is to set the size of the buffer data store. Everyone knows that the memory capacity of a GPU is usually not very large. Therefore, a reasonable allocation of memory is needed. Here's a number of bytes for vertex position data. Because each vertex component is a floating point, so I applied the for float 32-bit floating point array store data. Generally, 32-bit or byte storage is used for floating point data. The last parameter is to prompt webgl. We will use these datas. Because I was writing the vertex data here, I'll be using gl static draw. What is if it is a dynamically updated? Well, we can usually use the dynamic draw approach to define it. Next, start defining a film shader. The definition of the fragment shader is similar to the vertex shader, so you'll also need to define a coloring text. At the beginning, we declare all floating point precision, so I'll be using medium precision. Then let the fragment shader output a uniform color for all fragments. GL built-in variables is used. Frag color, it's also a vec4. In this, I choose to make it output. Usually the RGBA value we use is 0 through 255, and you need to normalize here from 0 to 1. So I am here, 1, 0, 0.5, 1, corresponding with RGBA values of 255, 0, 127, and 255, also known as rosy red. Then create a film shader. Also uses the create shader method. Select fragment shader here. Then associate our fragment shader text. This way we are configured with the vertex shader and the fragment. Next, we bind the vertex shader and the fragment to the coloring process. Similarly, I also define a function to create a coloring program at the top right. It receives 3 parameters. The first one is context, the second is the vertex shader, and the third is the fragment shader. Its operation steps are similar to create shader. Also create a shader at the beginning. Then let the current shader bind the vertex shader and the fragment shader. These 2 shaders are then bound to the coloring program. Finally, determine the status of the binding. Because this is a single function, so there's no way to prompt. You can only hit it. Then it is judged. If successful, it returns the current coloring program. Otherwise, it prints a failed log information. If you fail, you also delete the current coloring program. Then we create coloring procedures. At this point, the input vertex data has been sent to the GPU, and it indicates how the GPU handles it in the vertex shader. It's going to be completed, but hasn't ended yet. WebGL still doesn't know how to parse vertex data in memory. In other words, how to link vertex data to vertex shader properties. We need to tell WebGL how to do this. The vertex shader has a feature. It allows for the specification of any input in the form of vertex attributes. That is, a vertex can contain multiple properties. For example, our location attributes. This form of inputs provides us with a great flexibility in data organization. Because we only have the vertex properties here, so a float32 vertex buffer will be parsed into this. As you can see from this figure, each vertex location contains two positional components. Since the buffering is a float 32-bit floating point array, 1 byte is 8-bit digits. So a component takes 4 bytes and a vertex attribute takes 8 bytes. Offset represents the offset of the current input data in a vertex data. Since it's only the position in this vertex data, the offset is 0. If you have a vertex color, texture coordinates, or other things, then you need to select an appropriate offset according to the data structure. This offset is provided in the form of an X byte number of data offset lengths. Stride represents the total byte length of a vertex data, calculated as the vertex data length times the number of bytes. Let's say a vertex data has only one vertex attribute per position. The position has two components that use float 32 floating point data. Then the total bytes of the vertex data will be 2 times 4, which equals 8. After understanding these, we can start to analyze the vertex data, set up look before parsing, and conduct NDC coordinates to screen coordinates when screen mapping. The screen coordinates obtained by the screen map determine which pixels of this vertex corresponds to the screen. Eventually, these values are passed to the rasterizer for processing. Also, clear the color of the canvas and the color buffer can be set directly to transparent. I will facilitate the drawing area here, so it will set it to black. Since the colors that are finally presented on the screen are red from the color buffer, therefore, every time you draw, you have to clear it, otherwise it may appear again. Next, to enable coloring programs, enable the specified coloring program every time you draw. Remove the position index of the vertex position properties in the vertex shader. This index number is referenced in the list of properties of the GPU maintenance. So each time an operation is performed on an attribute, the attribute is activated. Then rebounded to the array buffer. This ensures that the buffer currently used by the array buffer is the vertex buffer I created. Then tell the property how to get the data. The mobilized interface is vertex attrib pointer. Let's take a look at the definition of every parameter at once. The first parameter index represents the location of the specified properties on the vertex shader. We've gotten a location of a position here. The second parameter size represents the length of the data to be taken for the content vertex data. I have submitted for every vertex here, so the quantity is 2. Type data buffer type. I use a float 32 floating point, so I'll use GL's float. Tell webgl the current data is a floating point. Normalize determines whether the data should be normalized. And because I have already provided to cut the coordinates, so it's not normalized. There will be a case study on the use of normalization in the next video to give you an idea. Stride represents the way to distort data stored. 0 indicates that the data is continuously stored. This is usually used when there's only one attribute data. For example, the vertex data we currently submitted is only a vertex position. Non-zero means that the interval size of the same attributes in the data can be interpreted at step size. This will be shared in the next video. The offset value of the attribute in the buffer at each interval, a unit is a byte. Because I have continuous data, so this offset value is still 0. Now, fill in all the content. The first one is the attribute location. The second is its size, 2. Then type float, normalized as false. Stride is 0 due to continuous, and offset is also 0 because it's continuous. After setting up all the top point properties, you can render it next. Here we call the drawing interface GL draw arrays. Draw arrays receive 3 parameters. The first is the pattern represented that we can draw, or the point is still the line or face. Since we're drawing a triangle, it's a face. GL triangles. If you're using a point, you can choose point. Or if you're using a line, choose line. The second is from which point that begins at. We default to 0. The third is to draw several vertices. Because we are a triangle, we need 3 points. So let's fill in these 3. Okay, here so far we have written our coloring code. Next, just run our script. So I'm here to make the script. Perform the main function directly when the script is running. Okay, let's run. Drag the HTML file directly on the browser. This is easiest debugging method. I found that there was no success, so let's open the console. Oh, wrong. Well, the vertex shader is broken. That's a problem. So let's take a look. This step has no problem. Then compile the shader. Here's the problem. After compiling shader, I have to get the status of compilation. As a result, the same method is used. Let's change. Then refresh it again. We still have an error and an error message. Frag color. Spelling mistake. I apologize. I made a big mistake there. I'll try not to do it again for the rest of the video. So this is fragments. Okay, let's try it again. Okay, no problem. You can finally see the triangle. We finally passed the first step of our rendering. Congratulate yourself for getting through this. In our next chapter, we'll deepen our education on this. But, today's content is the first of many. So we'll hope to see you in the next one.